All right, so I've got a 15 kilogram. It's 6 meters from the left end. There's a construction worker. The second worker is standing on the far right side. He is 75 kilograms. So it's 100 kilograms. And he's 6 meters, and then that's 15 meters. So far, so good? Safety rope should be attached to the center mass. Where should it be attached? Okay, so I look at this and go, oh, if I'm just going to do this, I'm going to go sum of MRs over sum of masses, right? So sum of MRs would be 100 times 6 plus 15 times 75 all over
I did it from the right side. That's why
175. It says from the left side.
Yeah, I realized that.
You're a rebel. If you did it from the right side, what'd you get?
You get 75 times 0 plus 11 times 100, right?
And what do you get?
By 175, and you get.
You should get like 5.
900 divided by 175, and you get 5.1.
What is that? The same distance measured from this side. Yeah. Good? What if it's not a light beam, is what the man said. He's absolutely correct. The way a light beam operates is we ignore its mass because it's not relevant. But if it is, this is no place to write this down. I just want you to listen. If it is a not light beam, in other words, a heavy beam, substantial, and they give you the mass for it, they're also going to use the word uniform. What does uniform mean? Same throughout, which means the center mass is going to be where?
Everywhere. Or in the middle. In the middle. In the middle.
In the middle. So what they're going to say is uniform. Uniform means the center mass is in the middle, which means you added additional torque. Its mass, which is the mass of the beam, mass of beam, right, is added in. And then the R, just like you would. You just add an additional object, which is centered at the center of mass, right? So we did the same problem with the guys on the beam. We have what? One guy at 6. What was it? One guy at 6 meters, and he was 100 kilograms. Then we had a 100 kilogram guy. No, we had a 75 kilogram guy. 15 meters from the end.
Yeah.
That's 15 meter beam. We would add an additional force, which would be right here at 7.5 from the end, and it would be the mass of the beam. What do you want to make the mass of the beam?
3,000.
Making the people on top irrelevant. Let's make it a 200 kilogram beam times 9.8. Oh, sorry, not times 9.8. So that'd be 200 kilograms, right? So when I do my center of mass calculation, I would do sum of all the MRs over the sum of the masses, which is 6 times 100. Whoops, 6 times 100 plus 75 times 15
Plus 7.5 times 200.
plus 7.5 times 200. That's all it adds in. If I'm doing a torque problem, like I've got a hinge here and I wonder how much torque it is, you just simply make this the radius that it's operating out of. Does that make sense? Good, because that's where we're going. Since we started that conversation. Good deal. All right, let's do it. Okay, equilibrium problem before, we'd have some sort of a block, a sign or something. We'd tie a rope to it here, and then we'd tie a rope to it here.
Oh, yes.
And then we would do what to determine how to do the problem? You're going to break them into up and down, left and right, and the net force has to be 0. And then last year, I don't know if you remember this, but I had the TA had written my problems and actually wrote a rope sitting here. And I said, please pretend like it's hanging off the end. What would happen if I put a rope there?
It would start hanging down.
It would start swiveling down, which means that to be in equilibrium, it has to be left, right, up, down, and the torque needs to be 0. The net torque. Some of all the torques has to be 0 as well. So you've got an additional thing to worry about. Make sense? What?
That was your TA last year.
This was years ago, the person who fixed it.
Oh.
She actually ironically became a physics major.
Really?
Yeah. Or she dropped out and became a government major. No discussion. Good?
Yeah.
So we're going to sum up the xy's, sum up the x's, sum up the y's, they have to equal 0, and our rotation torque also has to be 0. Now we have a huge advantage, tactically, and that's this. Where does it have to not rotate around?
The center of mass.
Center mass is 1 point, but what if I said it doesn't have to rotate around this point either? Would that be true as well? Or this point here?
I don't
It's
know.
not
Your
gonna
eyes.
rotate in general, it doesn't have to rotate around.
It doesn't matter what point right I pick. So you strategically pick your point. What do I mean by that? If you've got, and this is the traditional problem, you've got a pin here, you've got a stick sticking out like this, you've got a band of people playing musical instruments here, you've got a rope hanging here to hold the whole thing together. Okay? What is the place that has the hardest place to figure where what's going on force was? That pin right there, right? It's lifting. It's also keeping them from turning. It's also keeping them from going into the wall. That pin's a problem. So where are you going to set your torque to be? What's your initial radius for which your torque is going to be? Right there. So that R times it, what would the R be? 0, and so all the torques around, I don't care what the force is, it cancels out anyways. It's not my problem. Okay? So you're going to strategically pick the point which gets rid of the part that gives you the biggest headache. Make sense? Okay, so this is just strategy. Let's do a problem.
Oh, man.
I have a 5 meter long horizontal beam weighing, it weighs something. Which means it's got a center mass, which means I'm going to have to deal with that. It's going to use the word uniform at some point. It doesn't say that. That's kind of weird. Well, this was an AP Central question. This was from your textbook. Have you seen your textbook? We need them back in about 2 months.
I know where it is.
Yeah.
You know where it is. That's good. So I made that too close to the top. Hold on.
She's gonna have last year's one too, and probably not gonna get it back. To be honest.
Excellent.
Wait, how much did it cost?
They're about 120 bucks a piece.
I have mine. So.
I would assume so. All right, a 5 meter long horizontal beam is 5 meters long.
Are we assuming it's uniform?
You're gonna have to because it doesn't say anything, and it should say it's equilibrium. They will. AP Central will be really, really good about that. I'll try to be good about it too. 5 meters long beam. It weighs 315 newtons. So we're gonna assume that operates where? Out of the center mass, right? So it's 315 newtons. Attached to wall by a pin. Connection that allows the beam to rotate. Its far end is supported by a cable, which has an angle of 53 degrees with the beam, which creates a force tension there. There's a person standing on it, because that's what people do. They stand on beams. And he has a weight of 545 newtons.
That's a lot
I
of
thought it
newtons.
said 15 meters.
No, it's not. Yeah, that would be bad if he was that far. So he's 1.50 meters. That makes the problem much easier, though, to do, right? He wouldn't be on there. Not my problem. Find the force of the cable, Ft, and the force exerted on the beam by the wall if the beam is now at equilibrium. Okay, so we're going to do the same thing we've always done. Okay? We're going to sum up the x directions. We're going to sum up the y directions, and then we're going to do the torque. That's the new part. Okay, so let's do y first. In the y direction, force net equals the sum of all forces. Agreed? What's the force net got to be if I'm in equilibrium? 0. So I take a look at this. What forces do I have? Now this pin, does it push up necessarily? Possibly. Possibly not. Almost surely does, because if it doesn't push up, it's not attached to the wall, what happened? It would slide down. So it probably has some force in the upwards direction, which I'm going to call Fy. Bring it into components. So doing the components, I've got Fy starting from the left. That's up. I've got minus 545 down. I've got minus 315 down. And I've got a component here, right? So what would that component be? Plus Ft sine of 53 degrees?
Wait, why do we need to do force? Why do we need to start out like this? Why can't we just go straight?
We can do all three. We're going to do all three.
No,
It's got to be true for all three.
you can do one of the three.
You can do any one of the three you want to,
But you don't have to do.
but you're ultimately going to have to do all three, probably.
Oh,
If they set up the problem correctly, it's going to be too many unknowns to do it. You've got to. That's the reason why you got to attach the rope in the right place. We've been attaching the rope in the right place. Does it? That's a little different. So far, so good. Okay, so I simplify this. I get 0 equals, what does this become? -8, -860 plus Fy plus, somebody sign at 53 degrees fast.
Degrees.
Somebody check Mitchell because he gave me the first answer.
1.703. You
1.703.
guys know how to use that calculator?
Is it?
798.
0.798?
It's gone back.
How do you change, Nelson? How do you change this into degrees?
You go to
Yeah, I got you, Mitchell.
No, I have.
All right, enough. Let's go. Moving on. So I've got my Y direction. Can I solve this?
No.
No. Let's go X direction.
Right to dock?
Oh yeah, I know how.
X direction. In the X direction, I have to have 0 net force as well. What's pushing left, right?
The person.
The person's pushing left, right?
The wall.
Which way is it? Wait, straight down. Straight down. The wall is going to be pushing in this direction, right? Agreed?
Yeah.
So that we got an f of x to the right minus this component here, right? And that component there would be force of tension
Cosine.
cosine
Oh,
because it's pulling to the left. Yeah. One's got to be negative.
Assume that the pin is completely strong in both directions.
No,
Because if it is hanging, if it's not pivoting.
it doesn't matter. It has to do what it has to do to hold it in place. You can have a massive weight on it and very little. This cable could be pushing whatever. Now, again, if it was 45 degrees, then things get a little more interesting. It's 53 degrees, so maybe not. And you might be able to assume some proportionality. The problem, of course, is that these people walk back and forth. It changes it, so I doubt that's legit. Okay, so do the problem, and I do this, and I get 0 equals f of x minus, what is cosine of 53 degrees?
0.602.
0.602 force of tension. Can't solve that one either. Need a third equation.
Or couldn't you just solve the
Oh,
force of
man.
tension?
Wait, I have a.
How do you do that? Because I got Fy and Fx.
Well, you could just,
So I need a third thing. So now I'm going to,
Why is the f of x pushing outwards? Is because the force of tension is pulling in.
well, if this pin is not pushing outwards, what would this rope do to it?
Okay.
Right?
Yeah. Okay. Makes sense.
Now it's hard to imagine how it would hold it up, but not hold it in. I'm like, try to kind of think would do that, but that was what happened, right? And then it mounts force. Okay, so I got a torque net. Gives us a wall torque. So 0 equals. Now we pick a place we don't like. What's the place I don't like? Pin, right here. I'm going to say that's 0. So how much torque is that going to be? Then we're going to go F cross R plus F cross R plus F cross R plus F cross R. There's 4 forces on it, right? So starting from the left, we go 0 equals. The distance is R, so the pin provides how much force? 0. So that was torque. Sorry, I should have said. There we go. Second one would be 545. What's the distance? Times 1.50 plus. Next one.
3.5.
3.5. How long is B?
2.5. Sorry.
2.5. 2.5
Times 315.
times 315 plus. Now remember, it's a cross product, so I'm only going to pick up this component, right? The lifting part. So it's going to turn it. And by the way, this is going to be a negative when we're done because it's pushing the other way. These both want to make it rotate this way. This wants to make it rotate that way around the pin. So I'm going to go minus, and this is going to be 5 times just the component that is in the up direction. So that would be force of tension sine of 53 degrees, which we've already figured out what sine of 53 degrees is. That would be 0.7898 force of tension.
Did it say it was pulling up with 5?
No, it's 5 meters away. It's attached to the beam.
Oh.
We don't know what the force is that we're solving for. Make sense, sort of?
Yeah.
Okay, I'm going to pause.